Is our notes today are on 1.7. It's going to involve transformations of functions, translations, reflections, and also expansion, contraction. The notes are going to be somewhat extensive, so I'll do my best to consolidate and keep it as short as possible. If you don't want to do, for instance, this first part of the input-output table, you can simply watch what I do. So just to get an understanding of why the translations work the way they do, first off, if we graphed f of x, absolute value of x, that means that 0, 0, this is the f of x right here, 1, 1, 2, 2, 3, 3, and then negative 1 would give us positive 1, because absolute value negative 1 is positive 1, and then negative 2 would give us positive 2. We get this v as our parent function, as we saw last section, for a absolute value. Now let's look at what happens when we do absolute value of x plus 1. If I do negative 2, negative 1, 0, 1, 2, just to pick some values. If I now take negative 2 and insert it in, that would give us positive 2, but then we have a plus 1, which would then give us 3. If I insert negative 1 in for here, negative 1 absolute value would be positive 1 plus 1 would give us 2. 0, if I plug in 0, I'd have absolute value of 0 plus 1 is 1. And then absolute value of 1 plus 1 would be 2. Absolute value of 2 plus 1 would be 3. If I go ahead and graph that, I have negative 2, 3, negative 2, 1, 0, 1, 1, 2, and 2, 3. And we see that has shifted the graph up 1. So when we have this plus 1 or value on the outside, it shifts the function up. Let's go ahead and take a look at when it's on the inside. If we go negative 2, negative 1, 0, 1, 2. If I take negative 2 insert in, and we do negative 2 minus 1 first, gives us negative 3. Absolute value of negative 3 is positive 3. Negative 1 inserted, negative 1 minus 1 would give us negative 2. Absolute value of negative 2 would be positive 2. If we plug in 0, 0 minus 1 is absolute value of negative 1, which is positive 1. If I plug in 1, 1 minus 1 is 0, and then 2 minus 1 is 1. And let's go ahead and graph that. Compare it to our original. So we have negative 2, 3, negative 1, 2, 0, 1, 1, 0, and 1, 2. And we see our v right there. So if we compare this blue graph relative to the original parent function, it has shifted one value over, as that's supposed to be on 1, 0. That shifted to the right one. So we see when the addition or operation is on the outside, it moves it up. When it's on the inside, it moves it right. We'll talk about right-left nature as well as up-down nature. So what we see here is that when it's plus 1 on the outside, it goes up 1. That would mean if it's minus 1, it would go down 1, similar with plus 2, minus 2. When it's on the inside, when we think minus 1, we go, that means we move to the left. But in fact, we move to the right because this output of our original parent function is 0. So what would you have to plug into x to get out 0? 1. So that shifts it to the right. That's mathematically why it works. So we're on the inside, it goes in the opposite direction of what we intuitively think. When it's on the outside, it moves up in the direction that we would think. So now if we move over to this one, if I have a plus 2 on the inside, that means it's not going to move in a positive 2 direction to the right. It's going to move in a negative 2. And then we have a minus 3 that would move with it in the y direction. So it'd be down 3. So our coordinate then would be negative 2, 3 would be our vertex, quote-unquote vertex, or key point, as I like to call it, of the parent function, which is an absolute value function, and then we go ahead and draw our absolute value function from there. So this is what a cute little mnemonic device to remember this is called Spider-Man rules. It's called Spider-Man rules, and this works only for translations. That Spider-Man likes, so we're just going to make the prediction that Spider-Man likes to be outside. And when he's outside, he's happy. And then when he's inside, he can't shoot his webs and swing. That's why he's happy outside, because he can shoot his webs and swing from buildings. But inside, he can't shoot his webs and swing from buildings. So he's not happy on the inside. So if he's inside, we ask him to move C units, negative C units. He's not going to be happy and move and not listen to us and move the other direction. A plus c, we ask him to move positive c, he's not going to listen, he moves the other direction. When he's outside the function, we ask him to move outside, he's happy, so therefore he listens. We ask him to move up c, he moves up c. And if we ask him to move down c, we move down c. Now this is just a silly little analogy to help us remember the rules, especially it'll get important when we move on to trig functions where the translations will look a little more complicated in terms of the graphs, as you know, with like sine and cosine graphs. Also works here as well, I think. Okay, so now let's look at reflections. So if I have my basic f of x equals root x, 0, 1, 4, I like plugging those in to f of x, root x, and this is x. Could also have written f of x equals root x. We like plugging in perfect squares, so that, I'm going to graph that first. That'd be 0, 0, 1, whoops, not 1, 2. That'd be 0, oh, that is really bad, sorry. 0, square root of 0, 0, square root of 1 is 1, and then square root of 4 is 2. That's why I like doing perfect squares, because it just gives us nice, neat outputs. 1, 1, and then 4, 2. Whoops, 4, 2 up here. So there's our basic parent function, and now we're going to look at what happens when we translate it. G of x, I'll do that in green here. So I have x, and then I have negative root x. So if I plug in 1, 0, 1, and 4, that would give us square root of 0. Opposite of square root of 0 would be 0. Then the opposite of square root of 1 would be the opposite of 1, or negative 1. And the opposite of the square root of 4, note this negative's on the outside, will give us negative 2. So if I graph that, that would give us 0, 0, 1, negative 1, and then 4, negative 2. And if we look, the green graph relative to the black graph would be a reflection about the x-axis. So we see when we have a negative on the outside, and outside's associated with output, it reflects over the x-axis, which makes sense because it's an up and down movement, but we also want to have an efficient way of memorizing this. We'll talk more about that as we move forward. Now as we look at the next one, now when we plug in our inputs, if you look, if we plug in a positive 1, we would have root negative 1. So we have to plug in a negative 1 to get a positive 1 out. Furthermore, we're going to plug in a negative 4. So square root of 0 is 0, square root of positive 1 is 1, and square root of 1 is 2. And now we have 0, negative 1, 1, and negative 4, 2, which gives us a reflection about the y-axis. So now if we look at C, what we have is a plus 2, which is a shift to the left, and then this would be our axis of reflection, and then on the outside, again, excuse me, reflects down, so we'd end up having a graph that looks like this. That will make more sense as we move forward. So the way that the reflections work is if it's on the inside, a reflection on the inside, or on the outside, think of it as y values changing. So you're going from up to down or down to up, and that would, an up to down movement would be about the x-axis. A reflection on the inside would be a left to right, which is a reflection about the y-axis. So that's what we have right here. Reflection in the x on the x-axis is on the outside because that would be reflection up and down over the x-axis. That's how I like thinking about it, is the movement of the reflection. And then on the inside is left to right about the y-axis. Non-rigid transformations, if we first graph our parent function of f of x equals x squared, we would have 0, 0, 1, 1, 2, 4, and I'll just use the same one, comparing it to both of these. So if I have h of x here, I'm going to quickly do an input-output table. 0, 1, and 2. 0 squared would be 0. 1 squared times 3 would be 3, and then 2 squared would be 4 times 3 is 12. So 0, 0, 1, 3, and then 2, 12 would be off the graph. We see that condenses it horizontally. So I like thinking about it in terms of the horizontal change. So the graph gets shifted in horizontally or condenses horizontally. If it's a third, it's going to expand out because it's being multiplied by 3. It's going to look more like this relative. Whoops, not the best drawing. And of course, I can go through the input-output table with you on that if necessary. But when you're between 0 and 1, that expands the graph horizontally. And note, this also says, the first one says -1, less than -1. The negative flips it, but the fact that it's -2, x squared, etc., the absolute value of that coefficient, if it's greater than 1, is going to condense the graph. Now when we're doing transformations of a graph that doesn't have an algebraic equation associated with it, what we're going to do is first get the coordinates, and we have two ways of doing this. One way is actually doing the transformations on the numbers of the coordinates, or the other way would be visualizing the transformation graphically, and I'll show you what I mean by that. So first I'm going to list what these coordinates are, and then we're going to come over here and look at what function first they want us to transform. Negative x on the inside is saying the opposite x values, so that would be a reflection about the y. So if I come over here and I want to graph -4, I want to reflect about the y, I'm going to go 1, 2, 3, 4 units in the x, or towards the y, and now I'm going to go exactly the same distance in the opposite direction, 1, 2, 3, 4, which puts us at the coordinate 4, 2. And I do know that this graph is kind of scaled or zoomed in differently. This graph is zoomed in differently than that, but nonetheless we can still do the translations and reflections relatively easily. So this reflected about the y-axis is 6 units, 1, 2, 3, 4, 5, 6, and we're going to go 6 in the exact opposite direction, 6, 1, 2, 3, 4, 5, 6, which puts us at -6, 2. And another way you can think of it as is this means the opposite x value is going to produce out the same y value. So for this, we have 4, 2 instead of -4, 2, and -6, 2 rather than +6, 2. Let's try that method as well. We're going to have opposite x value that produces the same y value, so that'd be +2, -2, and then 0, -2. 0 doesn't reflect, so we have it right there. +4, and that's relative to this graph right here. We're just going to take each of these points and shift it up 4 values. This one we're taking the output and multiplying it by 2. So if we come over here, you multiply this output by 2, so -4, 2 would be -4, 4. -2, -4, as again, -2, -2, we multiply the output by 2. And then we have 0, -2 would be -0, -4. And then lastly, 6, 4. 1, 2, 3, 4. And if you see, that has been condensed horizontally. It's kind of harder to tell, but it is. So this one, the -4 on the inside, is saying move the graph. Remember, we're going to do Spider-Man rules, so we're going to move it to the right, and then we're going to reflect it. It's an up and down shift because it's negative on the outside. That's a reflection about the excuse me, that's a reflection about the x-axis. So my suggestion is to do these when you have multiple transformations, to do it graphically by starting out with the coordinate -4, 2. I'm going to put my cursor in -4, 2. I'm going to shift over 4 units first, 1, 2, 3, 4, and then I'm going to reflect it about the x-axis, would put us at 0, -2. I'm going to go to the next point, which is -2, -2. I'm going to start here. First thing I'm going to do is shift it over 4, 1, 2, 3, 4, and then over the x-axis puts us up there at 2, 2. And do the same here, 0, -2, move to the right 4, 1, 2, 3, 4, and then reflected about the x-axis would put us right there at 4, 2. And then the last coordinate, 6, 2. we're going to shift it over 4 units, 1, 2, 3, 4, and then shift it down, or I'm sorry, not shift it, but reflect it about the x, so it'll put us at 10, -2. And if you look at that, you just kind of take a step back and look, okay, if I shifted that graph over 4 and reflected about the x-axis, would that be correct? Yes, it would be. E and F, you can look at those in the completed notes. E would be just moving down 3. F would be multiplying the input by 2 and keeping the output the same. So now we're going to move on to writing an equation for the given graph. First off, we want to recognize what the parent function is. This is a quadratic. Quadratic starts here. So what's important is looking at the key point. Key point for a quadratic is its vertex. So if we have to get this vertex to this vertex, we'd have to move left 2 and down 1, which tells us that we have to move left 2, which would be a +2, right? Spider-Man rules on the inside. And it's squared because it's a parabola, and then we're moving down 1. And also, I'm just going to call this f of x, call it g of x, or any other name for the function, as it doesn't designate what it needs to be called. There's also a reflection about the x-axis, which means a negative on the outside. For the next problem, this is a cubic, so hopefully we recognize the parent function. I'm going to call it g of x just so it's different than the last problem. It's going to be an x cubed. Probably going to have a parentheses here in some capacity. So I'm starting out the crink in it, or the key point in the cubic function, starts at 0, 0. We go over 1 and up 3, so over 1 to the right would be a -1 on the inside, +3 on the outside. And there's also a reflection. Typically, a cubic starts down and goes up, so there's a reflection, and we're going to put that negative on the outside. Now, you may say that's a reflection about the y-axis. Well, let's see if we did that. A reflection about the y-axis would be a negative on the inside, like that. Now, if I cube this negative, cube negatives turns negative, which would give us that. So now, so in either case, whether you think of it as a reflection about the x or y, it would simplify to be the same. And then C, you can check in your completed notes. That's fairly straightforward, as it's 2 stations. Okay, now what happens if we have more than one translation and or reflection? Does the order in which we do them matter? There are 6 cases. There's cases of 2 reflections, or excuse me, 2 translations, 2 reflections, translation in the x, and reflect about the x, and then 3 more cases on the next page, which we'll get to. Now, I'm going to give you the reason we're using root x is we can see all of these translations and reflections with a root x, where we couldn't, for instance, with like a parabola. You can't see a reflection about the y. It would be exactly the same. A reflection about the y-axis would be exactly the same. Now, I'm going to give you the end game here. Case 5 and 6 is the only time that the order matters. So there's no work here. You're just looking at it and taking in what the rules are for conducting the translations and or reflections properly. So if I have my initial root x function, if I have 2 translations, if I translate left 3 and then down 2, this would be our final graph. Let's say I go in the opposite order, where I translate down and then over. In both cases, the graph is the same. Point being, the order in which you translate, whether you do the inside or outside first, you will get the same result. Secondly, with 2 reflections, this is a reflection about the y-axis and then reflection about the x-axis. If we did x or y over the y-axis first, then the x, we would get this as a graph. If we reflected about the x and then the y, we get the same. So when you have 2 reflections, the order in which you do them does not matter. If for the third case, where we have a translation in the x and then a reflection over the x-axis, so that's a translation on the inside and a reflection on the outside. If we translated left 3 first, we get this, and then reflect about the x, we get this. If we translate first and then we reflect first, then translate, we get the same graph. So the order doesn't matter. Now, if we have a reflection on the inside and a translation on the outside, if we first shift down 2 first, and then if we shift down 2 and then reflect, what would that look like? If shift down 2 and then reflect from this side over the y-axis to here, here's our final graph. For this one, if we reflect over the y first and then down 2, we end up getting the same graph in both cases. Now this is the order, and when the order matters, when we have a translation on the inside and on the outside. So first off, what I want to do is look at this, and I'm going to factor out, this is going to be our hardest case. What I'm going to do is factor out the negative on the inside. And I think if we factor out the negative on the inside, that gives more conceptual understanding for what we are going to do. So we're not going to pay attention to what we have here. What we're going to do is focus in on, if we do this, what is it going to look like? So if we follow our rules here, this would be a shift right and then a reflection about the y-axis. Now, if I draw my coordinate system here, if I first shift over 3, what you're then doing is also shifting the axis of reflection. So if I do that, first I shift over 3, my graph is going to look like this, but then I am shifting it about that axis, which gives us that graph. And note that does match up with the correct graph right here, which we could also check in our input-output table. So, point being is that when we have a reflection on the inside and outside, the order does matter. And the way that we do that, and why does the order matter? Well, we could do it in different orders. We could do the reflection first and then the translation, and we wouldn't get the correct graph. So what you're going to do is, when you have a reflection and a translation on the inside, what you're going to do is factor out the negative. You do the translation first. Imagine that axis of reflection is going to be translated as well, and then you reflect about that axis. And note we have the opposite of the x equals 3 axis rather than the x equals 0 axis. And the last problem down here, you see that order of operations simply applies. The reflection over the x goes first, and then minus 2. So you just look at it and say this is being multiplied by negative, and then subtract 2. So we have to do the reflection first and the translation second.